Hello, and welcome to lecture 3 of the course Symmetries, Particles and Fields. In this lecture, we're going to introduce Lie groups and matrix groups. Okay, so Lie groups are continuous groups, and so they have an infinite number of elements. So let's start off our chapter 2. So this lecture we will discuss Lie groups only, but we'll go on to discuss an alternative description of them really, which lies at the heart of them, called Lie algebras, but that's in future lectures. So as I said, Lie groups have an infinite number of elements. And these elements depend continuously on a number of real parameters. And this number is called the dimension of the group. So the various group operations, which is products and inverses, they depend continuously and smoothly on the parameters in a Lie group. So a Lie group G is a smooth manifold, which is also a group with these smooth group operations. And actually the dimension of this group is the dimension of the underlying manifold. So we write the dimension of G as dim G. And so this is the dimension of the underlying manifold. Now, we don't need to go into exact definitions of n-dimensional manifolds. The important thing for us here is that an n-dimensional manifold is everywhere locally isomorphic or equivalent to r to the n. So just n-dimensional Euclidean space. Let's give you some examples of Lie groups. just to get going. So for example, just Euclidean space or Euclidean vectors with addition is an example of a Lie group. So here, if we have some vectors and we add them together, we get another, so if these are n-dimensional vectors, we add them together, we get another n-dimensional vector, which is a smooth function of x and x prime. And so the inverse operation the inverse operation would be just minus x is also a smooth function. So this is a Lie group, and the dimension of this group is just n, the dimension of the space, the Euclidean space. Another example is our circle that we saw already in chapter 1. So this is defined to be the set of all real parameters theta, where theta is allowed to vary between 0 and 2 pi inclusive. But we identify theta equals 0 and theta equal 2 pi. So the group operation here is also addition. And we have that theta plus 2 pi is equivalent to theta. So notice that, globally, this doesn't look like Euclidean space, but locally, if we focus in on a tiny patch of a huge circle, it does look like r to the 1. So it is a one-dimensional manifold. We've got another description of this circle. We can describe it in terms of the complex numbers, where the modulus, or the size of the complex number, is 1. So S1 is Z is complex, and mod Z is 1. And here, complex multiplication is the group operation. Complex multiplication in group operation. And so there's an equivalence between these two portrayals in terms of the real parameter and this complex parameter, and there's an explicit map. And so the equivalence between these two portrayals can be seen by Z is e to the I theta. So of course, when you multiply to Z's to a Z and a Z prime, the equivalent thetas just add in the exponent. So subgroups of a Lie group can be discrete. So for example, we have the points 1 and -1, which is in this one-dimensional circle case. So this set of the points 1 and -1, they're just discrete points. They're in the circle, but they aren't Lie subgroups. So a Lie subgroup is a continuous subgroup and a smooth submanifold of the Lie group. So if subgroup H is a continuous subgroup and a smooth submanifold of the Lie group G, then it's a Lie subgroup. It's just a nomenclature, really. It's called a Lie subgroup. Okay, good. So now let's talk about matrix groups. So Lie groups of square matrices are important, and in fact, we're going to be describing Lie groups in these terms for particle physics applications a lot. So Lie groups of square matrices, I'll call these matrices M, big M. These are important. So here the group operation is matrix multiplication, and the inverse group operation is the matrix inverse. So matrix multiplication is the group operation, and the group inverse is the matrix inverse. So remember, one of the group axioms says that the inverse has to exist for every element. And so that requires that these matrices are non-singular. So in other words, the determinant of the square matrix must be non-zero. The identity element is obviously the matrix identity. So E is matrix identity, which we will label by I. So this is just the diagonal. It's a square matrix with ones down the diagonal and zeros elsewhere. So let's have a definition now of the general linear group. So this is written as GL n. So this is equal to the set of all n by n invertible matrices. And this is over some field F, and that's the field which fills the matrices. So in these lectures, we'll take F to be real or complex. That's going to be most relevant for our applications, but note you can take them to be quaternions or octonions as well. So the dimension of our general linear group. So we write it actually with the field explicitly. So if they're n by n matrices and each of the entries is real, then obviously we have n squared different parameters. So this is the real dimension. In other words, the number of real parameters. And if we have n by n matrices over the complex numbers, then the real dimension is n squared. For GL n over the real numbers. For GL n over the complex numbers, the complex dimension is n squared. But if we just say dimension, usually we mean the real dimension, which is the number of real parameters, and of course that's 2n squared. So it's important to note that we always have in mind that these matrices are going to act on some n-dimensional vectors. This will be important for our applications later on. So under the action of the group, these vectors go to v prime, which is m times v. That's the idea. So these groups will be symmetry groups acting on vectors. Excuse me. So there are various important subgroups. Of this general linear group. Let's take the case where the field is the real numbers. So first important case is this called the special linear group. This is written SL for obvious reasons, n over the reals, and this is the set of all matrices, n by n real matrices, where the determinant is equal to 1. So in other words, the special stipulation means that the determinant is plus 1. So what this does is this extra constraint on the determinant takes away one of the degrees of freedom. And so the dimension, the real dimension of SL n over the reals is n squared, just like the general linear group, minus 1, because we have this extra condition. And the real dimension of the special linear group over the complex numbers is 2n squared minus 2. Because really this, when we've got complex numbers, determinant m is equal to 1, if you think about it, is really two constraints over the real parameters. So this is the real dimension. So unless we specifically say complex dimension, whenever we quote dimension, usually we quote it in real, the real dimension. Okay, second important subgroup, the orthogonal group. So this is ON. So this is the set of all n by n matrices where m transposed m is equal to the identity matrix. So here we have, if you think about it, this is a matrix equation which takes away a fair few of the dimensions. And there's an exercise which takes you through how to work out how many dimensions this takes away. And so in the book or the example sheet, you'll see that this added condition removes n over 2 times n plus 1 dimensions. Again, real dimensions are implicit. So this implies that the dimension of ON is just the original dimension we start with, which is n squared, minus n over 2 n plus 1, which is n over 2 n minus 1. C exercise. So here, again, these matrices, of course, are going to act on vectors, and we note that the important thing about, one of the important things about the orthogonal group is that it preserves the scalar product between two vectors. The physical interpretation of this is that these orthogonal matrices are going to be rotations in n-dimensional space. Rotations and reflections, actually. So if we take two vectors v1 and v2, n-dimensional vectors, the scalar product is v1 transposed with acting on v2. So with an ON transformation, each one of these vectors gets transformed. So it goes to v1 prime transposed v2 prime. And so v1 transposed times m transposed is v1 prime transposed. v2 prime goes to m, is mv2. So of course this combination in the middle is the identity matrix, and we just get v1 transpose v2. And so this scalar product is invariant between the two vectors. And we note that our condition, which is that m transposed m equals I, if we take determinants of this equation, we get that the determinant of m is plus or minus 1 already. So now we have the special version of this, special orthogonal group, SON. So this is, let's call the matrices R, which is in ON, where the determinant now is plus 1. So in the orthogonal group, you can have both signs of the determinant, but when we have a special orthogonal group, the determinant is plus 1. And actually, just choosing the sign doesn't, this is a discrete choice, so it doesn't change the number of dimensions, which is about the number of continuous parameters. So the dimension of SON is the same as the dimension of ON, which is n over 2, n minus 1. Okay, so thirdly, we have symplectic group. So this is written SP, and we're going to do it for 2n by 2n matrices. So this is defined to be the set of all matrices, which are 2n by 2n, such that m transposed jm is equal to j, where j is a fixed matrix and it's sigma, it's of block diagonal form, which has sigmas down the block diagonals. Sigma is a 2 by 2 matrix and zeros everywhere else. Okay. So we have this condition. Again, it's a matrix equation. A big 2n by 2n matrix equation. And you can check for yourselves that the group closes. In other words, if you multiply two matrices which satisfy, two different matrices, each of which satisfies this condition, the resulting matrix also satisfies this condition. It's a one-line proof. So it turns out that the dimension of this group is n to n plus 1. So in terms of the vectors, what does this preserve? And actually, you can convince yourselves, again in one line, that V1 transposed times J times V2 is preserved by this transformation. So we also note that M transposed J times M is equal to J. So this is the condition on the matrix. If we take determinants of this matrix equation, we get that the size of the determinants of the matrix is 1. So it's, again, matrix determinant is plus or minus 1. Now, okay, so you can also define this for 2n plus 1 times 2, for odd dimension matrices, and that's when it is defined as in as we've just defined it, but with an extra row and column of zeros added on the bottom and on the right hand side. This isn't going to be so important for us today. So okay, so these are some real subgroups of the general linear group, where the general linear group is over the reals, but there are also some important subgroups where the general linear group is over the field of the complex numbers. And the first one is called Unitary Group. UN. So this is defined to be the set of all matrices U in GLN over the complex numbers, such that U dagger U is the identity matrix. And so U dagger is the Hermitian conjugate, which is probably familiar to you, but just in case it's not, it's that you take the complex conjugate and the transpose. So here in suffix notation, I've written it, you switch the rows and the columns and you take the transpose to find the individual elements. So this unitary group, when it acts on vectors, complex vectors, this preserves V1 dagger V2, where each of these is a complex vector. So this is important in quantum theory. So these unitary groups will be important to us because we're going to be dealing with quantum theories. And the reason is, so let's just, if we take a bracket of something and what happens is that the bra and the ket are related, are mapped to the vectors, the complex vectors, and then what happens is you get some V1 dagger, U dagger. So there's some unity transformation on the bra, and there's one on the ket. The bra gets a Hermitian conjugate, and of course, if U dagger U is I, this leaves the bra ket invariant. So that's an aside, that's why it's important. Okay, again, it's an exercise which is laid out in the book that to calculate the dimension of UN, and you'll find that the real dimension is n squared. Also important, it's going to be the special unitary group. So we take members of UN, but we additionally stipulate that the determinant is +1. Special unitary group. The dimension of this one is n squared minus 1. So that's the real dimension. And just for fun, although we won't be using them much, the symplectic group is the settable matrices in GL2n over the complex numbers, where M transpose JM is J, and the dimension is just twice the dimension of the real version. Okay, that's good. Now, there's another set of Lie groups, in fact, matrix groups, which are called pseudo-orthogonal and pseudo-unitary groups. These will also be important. So, okay. So the groups we've seen so far are examples of compact groups. Compact groups have a finite volume to their group manifold, and the natural parameters vary over a finite range. So let's talk about SON and SUN. These are examples of compact groups. Finite volume of the manifold, and the natural parameters vary over a finite range. So if I define a metric now, I want to define these pseudo orthogonal groups, which is just a bit of a generalization. So we define a metric matrix. So eta is going to be an n plus m matrix with block diagonal form like this. So I suffix n is an n by n identity matrix. So there's zeros elsewhere. So this is a pseudo-orthogonal group. Sorry, this is a metric which we can use to define a pseudo-orthogonal group. So this is written ON, M. So this is defined such that, so now M transposed eta M is equal to eta. So it's actually just like the orthogonal case, except now we have some minuses in, in some entries down the diagonal, whereas before we'd have only had pluses. And it's defined for n plus m across n plus m matrices. And so now this is non-compact. The group manifold has infinite volume. and some of the parameters can vary over an infinite range, the natural parameters. You can always, of course, transform parameters into a different, you can always transform them to get rid of that, but the natural parameters. So the invariant form of this group in terms of the vectors is V1 transposed eta V2. So as long as we form the dot product with this eta involved between two vectors, then you can prove to yourself that that's invariant very quickly. And all right, so the dimension of this group is actually just the same as the dimension of ON plus M. And that's kind of obvious, because if we put a plus here in front of the IM, then it's not going to change anything about how, we still have the same number of conditions that we stipulate to begin with. Okay, and so the unitary, pseudo-unitary groups are defined in exactly analogous manner. And so we have dimension of U, N, M, which is defined the same way with a U dagger, but with the eta. And this is dimension of the unitary group of N plus M, etc. So one of the reasons this is important to us, these particularly pseudo-orthogonal groups, is that Lorentz transformations can be described in terms of groups. And so this Lorentz group in special relativity, that's a pseudo-orthogonal group. Okay, let's just give you some more explicit examples of Lie groups now. Matrix Lie groups. So firstly, let's take SO2. So this is the settable matrices which depend on a parameter theta. And we can describe it in the following way. So it's 2 by 2 matrix. We have the following entries. And theta varies between 0 and 2 pi. So if you calculate the determinant of this matrix, you'll get 1 because the trigonometric relation. It's an exercise, very quick exercise for you to check that if you multiply two of these group elements together, you get another group element. And in fact, what happens is that these thetas add. And so this is proving closure of the group under the group composition. And so the interpretation of R theta is that it's a counterclockwise rotation in a two-dimensional plane. By an angle theta. Okay, so the group manifold is just this circle with radius 1. That's the same manifold as U1. Indeed, there's this map. We can use the ETI theta map. And so that means that these two groups are isomorphic. And we write the isomorphism, as we said before, like that. Okay, there's a very important group which we're going to cover now, which helps us actually analyze more general groups. And it's the group SU2. So it's going to be, there's an exercise in the book to show that this can be parameterized. So the exercise takes you through what to do to show that it can be parameterized by some group element, which is a 2 by 2 matrix, and we have complex elements like this, as long as mod alpha squared plus mod beta squared is equal to 1. To see exercise, where you can prove this. And so if we put alpha is a plus ib, where a and b are real, and beta is c plus id, where a, b, and c and d are real. So this implies that, so our condition here on mod alpha squared plus mod beta squared is 1 means that in terms of these real parameters, if we write that, you've got a squared plus b squared plus c squared plus d squared is 1. In other words, that's the equation of S3. So the manifold is S3. The group manifold is S3. And just for an example of an explicit example of a pseudo-orthogonal group, let's look at SO1, 1. So this is the set of all 2 by 2 matrices, cos theta, sine theta, cos theta. And now theta, this natural parameter, varies between minus infinity and infinity. Okay, let's give you one more example. And this is SO3, so this is rotations in 3 dimensions. So these are specified by some axis of rotation. So we're going to set this n vector to be 3 vector to be a of length 1, and an angle of rotation theta. So we've got effectively 3 real free parameters. So it's an exercise gone through again in the book. The elements of this matrix, so we're going to call the matrix R. So the ijth element, so I and j go from 1 to 3, can be written in the following way. See exercise. Minus sine theta epsilon ijk nk. So I'm going to call this equation 2.0. Now, this, all right, what does this mean? So epsilon ijk, this is the totally anti-symmetric symbol, three-dimensional anti-symmetric symbol. So epsilon 1, 2, 3 is equal to +1. And if you switch any two of these indices, you get a minus sign. What that means is also if any of the two of the indices are the same, the symbol is 0. So notice we've got a repeated index here. So I should say I, J, and K are in 1, 2, 3. And this, we're using the Einstein summation convention in these lectures. Unless I state otherwise, use Einstein summation convention. So repeated indices are summed over. So what we're going to do is we can think, sorry, yes, right. So we need to cover all rotations in 3 dimensions. So we can cover all rotations if n is in the 2-dimensional sphere and theta ranges between 0 and pi. So a rotation about an angle larger than pi is thought of as a rotation about -n. So we can combine all of these parameters into a 3-vector. And I can describe this 3-vector as theta times n. So theta n, if you think about it, theta goes up to pi, and n is a unit vector. So this is a ball of radius pi. In R cubed. But we have to notice that this ball's got some peculiar properties, which is a rotation through pi about n is equivalent to a rotation through pi about -n, which implies that the opposite points of this on the surface of the ball are identified. So if I draw a picture of this, we have, okay. So we think of this in R cubed, we have some ball. The ball has radius pi. But on the surface, any antipodal points are identified. So the crosses are identified, and say these circles are identified. So to summarize, SO3, the manifold, is a ball in R cubed, radius pi, with opposite points, let's say with antipodal points identified. Okay, that's good. So next time we'll put some coordinates explicitly on our group manifold. And then we'll be able to derive something about the inner structure of groups, which is called, of these Lie groups, which is called Lie algebras. And often it's easier to describe what's going on with the Lie groups in terms of the algebras. So this will be a kind of important structural lecture next time. Thanks for listening.